In this video, we're going to improve our estimate of the helium atom energy. We'll start by reviewing what we've done before with the helium atom calculations using the variational method, and then we'll use an improved trial wave function, which should get us much closer to the final correct energy of the helium atom. And at the end, we'll show off this best energy that we can get using the variational method and the improved trial wave function. So far, we've used the helium atom as a really good example of the variational method to compute the ground state energy of this insoluble analytical quantum system. The Hamiltonian for the helium atom has the kinetic energy for both of the electrons plus the Coulomb attraction to the nucleus for both of the electrons, plus the electron-electron repulsion. The simplest model we did in Chapter 5 was to ignore the electron-electron interaction, this one in green, completely, and put both electrons in the hydrogenic ground state with a spin singlet spin wave function. That function, the spatial function, is a product function of the ground state for electron 1 and the ground state for electron 2. And we know what those look like. They're just hydrogenic-like functions, except that we have to scale up z from 1 to 2, and so this is z to the third power. And then the energy that we get for that is just twice the energy of a single electron, and that's at minus 109 electron volts. When we did the problem including the electron-electron repulsion with this as our trial function in the variational method, we got an upper bound for the ground state energy, which was minus 109 plus 34, or minus 75 electron volts. So, this is where we stand. We have an upper bound estimate of minus 75 electron volts, but you can still do better with a more suitable trial wave function. And what was missing in the previous wave function was a variational parameter, something that we could adjust to minimize the energy. So that's what we're going to add now. We're going to add in a variational parameter and minimize. So let's look at this original wave function that we used for the last one, which was 8 over pi a cubed e to the minus 2r1 over a times e to the minus 2r2 over a. And we're going to adjust it. Instead of having 2 as our z that's hidden here, we're going to make a new parameter, z. And so our wave function, instead of wherever we had the 2 electron, or the fact that we had 2 protons in the nucleus, we now put z protons in the nucleus. And we have z cubed. Here we have e to the minus zr1 over a times e to the minus zr2 over a. And when we allow this to vary at the end to minimize, we're taking into account the so-called screening effect, which we did in a phenomenological or hand-waving way back in Chapter 5. But now we're going to use this as a variable parameter to minimize the upper bound energy. So this effective charge z takes into account screening of the nucleus by the other electron. So one electron will screen the nucleus from the other electron. If we go back and look at our Hamiltonian, I've reorganized it slightly here. So we have the kinetic energy, the potential energy excluding the electron-electron repulsion, and then the electron-electron repulsion here, which is e squared over 4 pi epsilon naught times 1 over absolute value of r1 minus r2. If I now add and subtract terms with z replacing 2 in the Coulomb terms, just these 2 Coulomb terms. So you can see I add e squared over 4 pi epsilon naught z over r1, and the same thing with negative z over r1, and then I add and subtract the same thing with z over r2 in these two cases. I can now rearrange this and make it a little bit more simple to solve. So the first thing I'm going to do is, looking at my trial function up here, I realize that this trial function can exactly solve the problem where instead of 2 here and ignoring everything else, instead of 2's here, we have z's here. So if I bring the two terms here, the minus z over r1 and minus z over r2, and replace here the 2 over r1 and 2 over r2, and then everything else remains over here at the end, this function can be solved exactly by this wave function. And that's what I'm going to do. So that sum of the non-interaction Hamiltonian matching this trial wave function, this is going to give me exactly the right solution. This is an eigenfunction of this Hamiltonian, plus an effective interaction term that includes everything else. And so what's left over, everything else, is all multiplied times e squared over 4 pi epsilon naught. But then we have the z minus 2, because we had to move this term over and move it over here, and over r1. And then we have plus z minus 2 over r2, because we had to move this term out here. And then, of course, we have our interaction Hamiltonian, 1 over r1 minus r2 absolute value. So now we know how to solve this, because we can just scale the solution for the hydrogenic-like atom to an effective value z. We also, so instead of the 8 in the energy up here, we have z cubed in the energy. And then what we have to do is do this integral here. So when we do the expectation value of the Hamiltonian, we have the first term, which gives us 2 times z squared, rather not z cubed, z squared times e1, where z is now an effective value. Then we have 2 times z minus 2, because there's two terms like that, times e squared over 4 pi epsilon naught times the expectation value of 1 over r. Those are the 2 Coulomb terms that are left over in the effective potential. And then we have this VEE sub EE, which we've already calculated before, which is the 1 over R1 minus R2 absolute value term. Recalling that the effective nuclear charge is Z, the expectation value for this term is simply Z over A. And the expectation value for V sub EE is the same as we just computed for the first attempt at the variational method using the helium atom, except that instead of 2 for our number of protons, we have Z. And so we can just go through that same calculation, and we get that we have the expectation value for V sub EE is 5Z over 4 times E squared over 8 pi epsilon naught A. So we have to do no further integrals for this. And this gives me minus 5Z over 4 times E1 being the energy of the ground state of the hydrogen atom. So the final result can be written like this. Everything is in terms of E1. So we have 2Z squared, that's from this term, minus 4Z times Z minus 2, that's from this and this term here, and including this, which is related to E sub 1. And then we have minus 5/4 Z, and all of this is times E sub 1, which of course is negative 13.6 electron volts. We can now multiply this out. We get another term with Z squared. Negative 4 and 2 gives us a minus 2Z squared. We have a term here that gives us 8Z, and here we have 5/4 Z, negative 5/4 Z. We end up with 27/4 Z, all times E1. Now, using the variational method, we now minimize with respect to the effective charge, z. So we take the first derivative of the expectation value of the Hamiltonian with respect to z. And this is d by dz of minus z squared, 2z squared, plus 27 quarters z, all times e1, which is just a constant. This gives me minus 4z plus 27 quarters, all times e1, and that's equal to 0, which means that z is equal to 27 over 16. Now remember, z is nominally 2 here, and so this is a little bit less than 2. This would be 32/16 would be exactly 2. And this is 1.69. So the improved energy estimate is now plugging this value of z, 27/16, back into our calculation for the estimate of the upper bound for energy is 2 times 27/16 squared minus 4 times 27/16 times 27/16 minus 2 minus 6 quarters times 27/16, E1. And this gives me, when I multiply all this out, I get 2 times 27/16 squared E1, or 1/2 times 3/2 to the 6th power E1, or minus 77.5 electron volts. So now let's compare the different solutions that we have with the experimental value. So the experimental helium energy is minus 78.975 electron volts. Ignoring the electron-electron interaction altogether, we get minus 109 electron volts. That's a 38% error, unacceptable. With a simple variational function, we reduce this error to about 5%. Again, notice that this is more negative, but using the variational method, we are less negative than the actual value. We're always above the actual value of the energy because the variational theorem tells us we have an upper bound on the energy. But it's still off by nearly 4 eV. Finally, with the variational z parameter, we get down to minus 77.5, which is closer by 2.5 eV. And so we're down to about a 2% error. So that's pretty good for one variable parameter.